Welcome, this is Professor Ridge, and today's lesson 7.1, Systems of Linear Equations, Two Variables. And today's first learning objective, solve systems of equations by graphing. Introduction to system equations. A system of linear equations consists of two or more linear equations made up of two or more variables such that all equations in the system are considered simultaneously. If you cracked open a older textbook, and a lot of older textbooks, they would call this systems of simultaneous linear equations, just to kind of emphasize that point. Okay, to find the unique solution to a system of linear equations, we must find a numerical value for each variable in the system that will satisfy all equations in the system at the same time. Some linear systems may not have a solution, and others may have an infinite number of solutions. In order for a linear system to have a unique solution, there must be at least as many equations as there are variables. Even so, this does not guarantee a unique solution. So if you want to find a unique solution, the idea is if you have two variables, you need to have at least two equations. And to get a unique solution, there's this idea that we talk about independent equations. So you need two linearly independent. You don't need to know that quite yet. Okay, and in addition to considering number of equations variables, we can categorize systems of linear equations by the number of solutions. So a consistent system of equations has at least one solution. A consistent system is considered to be an independent system if it has a single solution, such as the example we just explored. So back in the text, if you want to read about that. The two lines have different slopes and intersect at one point in the plane. So a consistent system is considered to be a dependent system if the equations have the same slope and the same y-intercept. In other words, the lines coincide, so the equations represent the same line. So basically they're the same line. And every point on that line, as it says here, every point on the line represents a coordinate pair that satisfies the system. So every point on the line makes both statements true, both equations true. So that would have an infinite number of solutions. Okay, and then another type of system of linear equations is inconsistent systems. So consistent has at least one solution. It can have one solution, so that would be an independent system. And then if it has infinitely many solutions, that would be dependent. Okay, now inconsistent has no solutions, and that represents two parallel lines. They'll have the same slope but different y-intercepts. Okay, and again, from geometry, parallel lines have no points in common, so there's no solution to the system. Okay, so inconsistent systems, no solution. Consistent can have one solution or infinitely many, depending on if it's independent or dependent. Independent are two intersecting lines. Dependent would be two lines that are actually the same line. And then inconsistent would be no solution, and there will be parallel lines. So here's a summary of what we just talked about. So the three types of systems of linear equations, two variables, and three types of solutions. An independent system has one solution, one ordered pair, right, an x and y that go together. The point where the two lines intersect is the only solution. So that's this picture here on the left. You can see you have two equations. When you graph them, they make two lines. Linear equations, remember a linear equation and two variables, when you graph it, makes a line. So we have two lines. They intersect at a single point, and that would be this ordered pair would correspond to the solution for that system. Okay, inconsistent has no solution, so that's this middle one, and they're parallel lines, so they won't have any points in common, so there won't be any ordered pair that makes both equations true at the same time. Remember, simultaneously. And then the third type is a dependent system that has infinitely many solutions. The lines are coincident. Okay, they're the same line. So every coordinate pair on the line is a solution to both equations. So both equations, basically, when you graph them, they make the same line. And also, remember, if it has one solution, at least one solution, it's consistent. So the independent system here would be consistent, and this dependent system would be consistent, right? Because it has infinitely many solutions, which is definitely at least one, right? Okay, and then again, the parallel line would be inconsistent. All right, so given a system of linear equations and an ordered pair, determine whether the ordered pair is a solution. So the technique is you're just going to substitute the ordered pair into each equation separately, work them out, and determine whether the statements are true, right? Whether true statements result from the substitution in both. And if it does, then that ordered pair is a solution. So basically, you just substitute. You plug it in, plug in the x and y into each equation, see if you get a true statement for each equation. And if it's true for both, see, that's the key word, both, then it's a solution. All right, let's try example 1. Determine whether the ordered pair 5, 1 is a solution to the given system of equations. In a lot of books, you'll see when they do a system, they'll put a brace over here like that. Some books do, some don't. So we're thinking this as a system together. So we're going to plug in 5, 1 into both equations. So if I call this line 1, I like to do it like that. So line 1, I'm going to put in 5 for the x, 1 for the y, and I put my question mark here. Want to see if this is true or false. So 5 plus 3 equals 8. That's true. Okay, so that one checks out, right? We get 8 equals 8. Now 2, now we do the second equation. We're going to put in the 5 for the x. We're going to put in 1 for the the y, for the y, and then check to see if this is a true statement. So we get 10 minus 9, which equals 1. That's definitely true. 1 equals 1. So it's true for both. So then that means that 5, 1 is a solution to the system. Oops, solution to the system. Okay, so you know how much I like Desmos by now, hopefully. So we can check this too. If I graph both lines on Desmos, and then I can click and see the intersection points 5, 1. So again, remember, every ordered pair on this line are solutions to, which one is this one? This one is solutions to the, it's the red one, so it's this one. So for instance, 0, 2.6667 would make this a true statement. So every point on this line is, on the red line, is a solution to the top equation, equation 1. Every solution on the blue line, every point on the blue line is a solution to equation 2, and they share one point in common, and that's the solution to the system. Okay? And that brings us to our first technique of solving systems of equations by graphing. So you can graph each line. So there are multiple methods of solving systems of linear equations. We're just going to go over a few of them in this in our course, but the book has a few extra that we won't be going over in my course. Anyway, so one of the methods is by graphing. So basically, you just graph each line on the same coordinate plane. So for a system of linear equations, 2 variables, we can determine both the type of system and the solution by graphing the system of equations on the same set of axes, right? On the same coordinate plane. All right, let's try one. All right, solving a system of equations, two variables by graphing. So here's our two equations. We'll call this equation 1 and equation 2. So equation 1, I'm going to put it in slope-intercept form, so subtract 2x. Now we can type this in decimals and just look and it'll be done, but you should be able to, you should practice a little bit doing it by hand. It's a good technique. So we subtract 2x, so if you remember slope-intercept form, this is where it crosses on the y-axis. Oops. So I need to make my graph a little bit bigger. So it crosses the y-axis at -8, and then my slope is -2. So if my slope is -2, I can write it as -2 over 1 or +2 over -1. So I can go up to left 1, sorry. Up to left 1. Up to left 1. Up to left 1. Up to left 1. And I like to do as many plots as I can fit on my graph, or points, just to make the graph a little more accurate. So there's my line 1. Actually, make it a little bigger. Okay, so that's my line 1. That's the line 1, the 2x plus y equals -8. Now let's do line 2. I'm going to subtract x and then divide everything by -1. So y equals x plus 1. So the y-intercept's 1. So 1, and the slope is 1, which I can do 1 over 1. So I can go up 1, right 1, up 1, right 1. And then I can change both the top and bottom, the signs of the top and bottom. So that's the same thing as -1 over -1. So that's down 1, left 1, down 1, left 1. Down 1, left 1. You can see they intersect at that point. Okay, so that's enough. I can figure out my answer here. So this one's line 2. Line 2, which is the x minus y equals -1. And again, every point, not just these nice ones that I did here, every point on this line is a solution to that equation. Every point on this line is a solution to equation 1. And this point where they intersect, that's common to both. And that's a solution to both equations at the same time. And that is my solution to the system, which is -3 for x, -2 for y. So my solution is -3, -2, right? And I like to put it in a solution set. So using braces for it's the set that contains the 1 point, -3, -2. Okay, the next method is, next learning objective is solve systems of equations by substitution, which is our next method. Okay, so the technique then is your first step is going to solve one of the two equations for one of the variables in terms of other. Basically, you want to get one of the variables all by itself, so like y equals and then everything else, or x equals and then everything else. So do that for either equation, doesn't matter which one. Then you're going to take that expression, so if it's x equals, say x equals y plus 7, right? Then you're going to take that y plus 7 and plug it into the second equation for the x, and then go from there. So step 2, basically what I just said, substitute the expression for this variable into the other equation, the second equation, then solve for the remaining variable. Okay? Let's do those two steps first. So we can take it doesn't matter which equation you start with. I typically look for the easier one to work with. So I'm going to work with 1 and solve it for y instead of x, because this is plus y, and then I'm just going to add x to the other side. So for equation 1, I'm going to add x to both sides, so I get y equals x minus 5. And then I take this expression, x plus 5, and I'm going to substitute it into the other equation, the second equation, for y. So y is equal to x minus 5. I'm going to take this y out, and I'm going to substitute the x minus 5 into that equation. So I'm going to take 2x minus 5y. I'm going to take the y out, equals 1. Right? So 2x minus 5y. I'm going to take that y out, and then put in y equals x minus 5. So that's the substitution step. That's the key step, right? If I said, hey, solve this by the substitution, that's the step I'm looking for, as well as the right answer. But anyway, okay, so distribute the negative 5. We're going to solve this resulting equation now. That's our step 3 up here. Or no, the second half of this one. Solve the remaining variable. So we're going to solve for x now. So negative 5 times negative 5 is positive 25. And then combine like terms, so we get negative 3x. Okay, and we're going to go up to here. So we got negative 3x plus 25 equals 1. So subtract 25. So negative 3x equals negative 24. Divide by negative 3. So x equals 8. All right, so now again, remember, we're looking for an ordered pair. So a solution is an ordered pair, an x and a y. So we just found a portion of the solution. So now you have to take this result and substitute that solution into either of the original equations to find the value of the first variable. If possible, write the solution as an ordered pair. Check the solution in both equations. Now it says you in the original equations, but I tend to put it in the equation that I solved in terms of the other one. So I'm going to actually put it into this equation. So I'm going to go back to equation 1, but the solution, the one that I solved for y, x minus 5, so I'm going to plug the 8 into there, substitute it. So 8 minus 5 is 3. So now my solution is 8 for x, 3 for y. And again, I like to use solution sets, or you can box it, that's fine too. And then if I want to check it just to make sure I did it right, you can you can graph this in Desmos and just click on it and see that it's 8.3, or you could do the algebraic check, plug it into both equations and see if it makes it true. So if we plug it into 1, you get negative 8 plus 3. Oops. Does that equal negative 5? So negative 8 plus 3 is negative 5. So that's true. And then if I check it in equation 2, 2x, x is 8, minus 5 times y, does that equal 1? So just, normally when I check it, I just type this, normally I wouldn't write it down, I just type it in my calculator. 2 times 8 minus 5 times 3, hit equals, so we should get 16 minus 15, which is 1. 1 equals 1, so that checks. So then I know I did it right. All right, and then the next learning objective is solve systems of equation by addition. Some books call this method addition/elimination. Some books call this method just elimination. Right? They're all the same method. Okay, so the technique for the elimination method, or the addition method, or whatever you're used to calling it, your first step is you want to write both equations with the variables on the left side and the constants on the right. Okay, write one equation above the other, lining up corresponding values. If one of the variables in the top equation has the opposite coefficient of the same variable in the bottom, then you just add the equations together, and that eliminates, see, that's why it's also called the elimination method. That's the goal. You want to eliminate one variable. If not, use multiplication by a non-zero number so that one of the variables in the top equation has the opposite coefficient of the same variable in bottom equation. Then add the equations to eliminate the variable. So again, that's the key. We want to eliminate a variable. So let's start with those. So the first step's done for us. And again, I'm going to label this equation 1, equation 2. Now notice, if I take equation 1 and equation 2 and add them together, the x's will cancel. So you're adding, basically you're adding the left sides together, you're adding the right sides together, and we just add down the columns. But what we're, again, what we're really doing is we're doing x plus 2y plus negative x plus y equals negative 1 plus 3. So we're adding the, since these are equal to each other, you can add this number to the left side, this number to the right side, since those represent the same number, if it's true. Then you get this equation. Okay, so we don't write it that way. That makes it a little more complicated. You can just add down the columns like you were doing an addition problem. So you just add down negative x plus negative x is 0. We don't have to write anything. 2y plus y is 3y. Negative 1 plus 3 is 2. So that's our solution. I mean, that's our addition or sum of these two equations, and it eliminated the x. So we can see we have an equation with one variable. I'm going to call this equation 3. Okay. Now I'm going to solve that resulting equation for the remaining variable. So I'm going to solve equation 3 here for y. So then I'm going to take both sides and divide by 3. So y equals 2/3. Okay. Now we're going to use the substitution method and substitute that value into one of the original equations to get the and solve for the second variable. So I'm going to take equation 1 or 2. Let's take equation 1. So we get x plus 2y. Take the y out, put in the 2/3 equals negative 1. And then solve it for x. So remember, if you have 2 times 2/3, you can write 2 as 2 over 1 and multiply across. So you get 4 over 3 equals negative 1. And then subtract 4/3. So x equals, and then negative 1 is the same thing as negative 3 over 3. Negative 4 over 3. So we get negative 7 over 3. So our solution then will be x is negative 7/3. Y is 2/3. And then I'm going to check. And typically what I do for the check is I just type it in a calculator. Let's see here. So I'm going to put in, so x is negative 7/3. And then plus 2 times 2 divided by 3, and then hit equals, or enter in this case, and I get negative 1. So see, that's the check. So I don't actually write down my check. I just do it with a calculator like that. And then do the next one. So negative a negative 7/3. So in my head, I know that's going to be positive 7/3 plus y, which is 2/3. Oops, got to pay attention to what I'm doing. So 7/3 plus 2/3, which would be 9/3, and 9/3 divided by 3, 9/3 reduces to 3. Right? Check. So even if you're not good at fractions, you just type it in a calculator and you're fine. And then another way I could check it again would be I can graph it on Desmos and see that they intersect at that spot. But Desmos usually doesn't show you the fractions. They'll show you decimals, so you have to recognize the decimal equivalent. All right, let's try another one. Now on this one, if you were to add the two equations together to get equation 3, you get 3x plus x is 4x, 5y plus negative 2y is positive 3y, and then negative 11 plus 11 is 0. But that doesn't help because we still have two variables. We want to eliminate a variable, remember? So what we're going to do is you want to make one of them have basically when you add them, you want to get 0. So if we have something x and 1x, we want to add these two numbers to get 0x. So basically I need to make them the same number but opposite signs. So it's like asking, what would an LCD of these two numbers be, or LCM, I should say. And you just kind of think through it. So if I want to get rid of x, I want them to be the same number but opposite signs. So if I multiply this one by 3, that would get me 3, and that's 3. And then I just need to make one of them negative, so I can multiply this by negative 3. Now, because it's algebra and this is an equation, you can't just multiply by negative 3 unless you multiply it with the whole equation. So I'm going to multiply the whole equation by negative 3. And I'm going to leave this one alone. Oops. I don't know what I did there. Okay. So I'm going to take equation 1, equation 2. I'm going to leave equation 1 alone. This is kind of the notation, so I can, when I look back, I can say, okay, what did I do? So this, I did nothing to equation 1, just write it down. And then I'm going to take equation 2 and multiply it by negative 3. So you get negative 3x. You got to do it to each term. Positive 6y and negative 33. And then this is going to create my new equation with eliminating the x. So 3x minus 3x is 0x, which is 0, so it goes away. 5y plus 6y is 11y. And then this will be negative 44. Now you're going to solve this resulting equation. So divide both sides by 11 to get y by itself. So y is negative 4. Then we're going to substitute this in either to equation 1 or equation 2. Let's do it in equation 2. So x minus 2y, y is negative 4, equals 11, and we solve for x. So negative 2 times negative 4 is positive 8. And then subtract 8. So x equals 3. So then our solution set consists of the single point, the single ordered pair, 3, negative 4. And we can check it. We can check it with a calculator. We can check it on Desmos. We can check it by hand algebraically. So let's do that since we haven't done that in a while. So if I do 3 times 3 plus 5 times negative 4, and here normally I would just type this into my calculator and hit equals and see what I get. So I get 9 minus 20, I get negative 11. So that one checks. And then I'm going to check equation 2. So 2 would be x is 3 minus 2 times y, which is negative 4. And then I'm checking to see that that is equal to 11. So we get 3 plus 8, which is 11. So that one checks. Okay, for example 6, you have to multiply both equations by a number to cancel out a variable. So you have, your first thought is, do you want to get rid of x or do you want to get rid of y? It doesn't matter. If you're looking at y, you can say, well, I can get rid of the y's easier because one's positive, one's negative, so I just got to multiply by positive numbers. But the 2 and 5, they're a little bit smaller. So if you think about what would be an LCD for 2 and 5, or an LCM, you could say, well, that 10. So I'm going to multiply equation 1. I want to get 10x and negative 10x. That's what I'm going for. So I'm going for 10x and negative 10x. So when I add them together, these cancel out, right? Or if I wanted to get rid of the y's, I would have to make them 30y. So I would have 30y and negative 30y. Okay? I chose to get rid of x. So 2 times what would get me 10? So that'd be 5. And then you multiply it with everything. So you get 10x plus 15y equals 80, negative 80. And then this one I want 10x, so I'm going to multiply by 2, but we want negative 10x, so it'll be negative 2. And then negative 2 times 5x, negative 10x. Negative 2 times negative 10 is positive 20y. And then that would be negative 60. We add, those cancel. We get 0x. 35y equals negative 140. Now we're going to divide both sides by 35. And then we get y equals, what's that? 3, 4, 4, negative 4. Okay, now we're going to take this y equals 4 and put it into equation 1 or 2. Let's do it in 1. So we get 2x plus 3y. Take y out, put in the negative 4. And we solve it for x. 3 times negative 4 is negative 12. Add 12 to both sides. So 2x equals 4. And then divide by 2. Oh, that should be negative 4. And then x equals negative 2. I should make a mistake on one of these and show you when I check it. You'll see that it's important to check, and then you'll catch that mistake like I almost made there. All right, so we get negative 2, negative 4. Let's check to make sure I didn't make any other mistakes. So equation 1, 2 times negative 2 plus 3 times negative 4, does that equal negative 16? So I just, in my calculator, 2 times negative 2 plus 3 times negative 4, so negative 4, negative 12, and hit equals, and it should be negative 16. Okay, the second equation, 5 times negative 2 minus 10 times negative 4, does that equal 30? So we got negative 10 plus 40, which is 30. That one checks out too. So I know I did it right. Okay, example 7. With this one, if you have a fractions in there, what you can do is like an intermediate step to clear the fractions first, is what I usually do. So like for this one, I'm going to look for the LCD for 3 and 6. And I'm going to multiply everything in this one by the LCD of 3 and 6 and get, which is 6. And I'm going to get 6 times x divided by 3 would be 2x. 6 times y divided by 6 would be y, because the 6 is canceled. And then 6 times 3 is 18. So I'm going to call this equation 1 now, my new even though this is the original equation 1, but this is my new equation 1. And then this one I'm going to multiply by the LCD for 2 and 4, which is 4. And this will be my new equation 2. So 4 times x divided by 2 would be 2x. 4 times y divided by 4 would be minus y. And then 4 times 1, that's a 4. 4 times 1 is just 4. And look, the y's are going to cancel, so we don't have to do another step to get, like we did in the last problem, to get two of the coefficients to be opposite signs in the same number. All right, so if we just add these, 2x plus 2x is 4x, plus y minus y, those would cancel. And then 18 plus 4 is 22. And then divide both sides by 4. We get, you can reduce this, divide by 2, so you get 11 halves. Now we're going to take this answer, we'll plug it into the new equation 1. So 2x, x is 11 halves, plus y equals 18. So here the 2's cancel, and then subtract 11 from both sides. So y equals 7. So our solution is 11 halves, 7. You can check it with the calculator. And just to emphasize, we haven't done one on Desmos in a while. Let's put in both equations in here and see where they intersect. So we got x over 3 plus y over 6. That equals 3. And then we got x over 2 minus y over 4 equals 1. And let's see where they intersect. That's why I like Desmos too. I can move things around. So I get 5.5, which is same thing as 11 halves, right? If you did 11 divided by 2, 11 halves, you get 5.5. 5.57, which is what we got. 5.5 or 11 halves, 7. Okay, next learning objective, identify inconsistent systems of equations containing two variables. Okay, so we know that inconsistent systems are parallel lines. Let's go back to that. So one way we could do it, if we were to graph these and you got parallel lines, it's going to be inconsistent, right? So parallel lines have the same slope in different y-intercepts. So if you had both equations in slope-intercept forms, they had the same slope and different y-intercepts, it's going to have no solution. That's one way. Another way is, what if you're just doing it algebraically, trying to solve this, either with a substitution or elimination, doesn't matter which method. In fact, we'll probably do it with both, just to show you that it doesn't matter which method you're using, you can recognize if you have no solution. So if you're doing algebraically, look at this setup for substitution. I can just take this 9 minus 2y that's equal to x and substitute it in equation 2. So I get 9 minus 2y for x. And then I can drop the parentheses. So the minus 2y and the 2y is 0. So those cancel. And you just get 9 equals 13, which this is false, right? And there's no variable. So whenever you're solving algebraically, whether either doing substitution or elimination, if you ever get to a point where you end up with an equation that has no variables and the statement is false, then this is going to have no solution, right? So the system is inconsistent. Now, if you were to get like a true statement here, like 5 equals 5, which we'll cover in a minute, then that would mean that it's always true for that statement. So that would tell you that the system's not going to be always true, but it will have an infinite number of solutions. Okay, so we'll get to that in a minute. All right, so I said it doesn't matter what method you used. If you were to rewrite equation 1, you add 2y to the other side. In equation 2, let's times it by -1. So you get -x, -2y, and 13, -13. You see how the x's cancel, the y's cancel. You get -4, you get 0 equals -4, which is false. It's always false. So same thing, you're going to have the same no solution inconsistent, right? So basically no solution. All right, so that's how you tell when you're doing algebraically. So if all the variables fall out and you end up with a statement that's always false, then you have an inconsistent system and it'll have no solution. And our last learning objective for today, express the solution of a system of dependent equations containing 2 variables. Example 9, find a solution to a dependent system. So dependent. So remember, dependent solutions. Let's go back and look at that. Dependent systems are basically the 2 equations represent the same line. So there's an infinite number of solutions. Every point on this line is a solution to the system. So how does it look when you're doing algebraically? What happens? So if you remember when we did the inconsistent system, you ended up with a false statement. So all the variables canceled out and you get a false statement. For this one, all the variables will cancel out and you'll get a true statement. It'll be like 9 equals 9 or 0 equals 0. Okay, so if you get that situation, that means it's a dependent system and you have an infinite number of solutions. Now that's typically all you had to say in elementary algebra or intermediate algebra, but now we want to represent the solution, even though there's infinitely many, and typically you can represent it as a point for your solution set. So it's going to be, what you do is your set builder, if you do it fancy way. So you have your x and y, your set of all x, y, such that you write the equation down. That's one way to do it. So y equals mx plus b. So that'd be one way to represent the solution set. Another way would be you just say it's set of all, and then you do x, and then if you solve, if this represents the same equation, you can solve one of them for y, and then this equation would be mx, y is equal to mx plus b. Okay, and that would represent all the ordered pairs that make that line. So typically you could do it either of these 2 ways. I think this book's going with the bottom one. All right, so let's try it. So we got equation 1, equation 2. We're going to do elimination method, or addition method, this book calls. So we want to cancel, let's cancel the x. So if I take equation 1 and times it by -3, you get -3x minus 9y equals -6. And equation 2 we're going to leave alone. And you can see quickly that, oh yeah, that's going to get me everything canceled. So we get 0 plus 0 equals 0. So, right, this is always true. Now, the system isn't always true. Only the points on the line. So, for instance, if I were to graph this is not the line, but if I were to graph this, both lines would be the same line, and only the points on the line are solutions to the system. So this point, like right here, 5, 2, is not a solution to that system. So this statement's always true, but that, remember, what we're doing here is We're trying to find the solution to this system of equations. So when you get this, it tells us, okay, so this is a dependent system. So that tells us there's infinitely many solutions. They're all the points on the line. So if we want to write the solution set, we're going to do x, comma, and we're going to write y in terms of x. So you need to take one of the equations, doesn't matter which, since they're the same equation. So I'm going to put it in slope-intercept form. So subtract the x. And then divide by the 3. So y equals negative 1/3 x plus 2/3. And that will be my y. So negative 1/3 x plus 2/3. And that'll be my solution set. Okay, so every point, so x can be any real number. In fact, sometimes you might write that, right, where x is any real number. So x is any real number, and then y is negative 1/3 times whatever x is plus 2/3, and this will generate all the points that are on the line. That's the solution to this system. All right, let's look at an example, example 10. So this is a finding the break-even point of the profit function using substitution. So given the cost function, c of x is 0.85x plus 35,000, and the revenue function is r of x equals 1.55x, find the break-even point and the profit function. So basically what we're doing here is we're going to, the cost function, here I'll just do a super crude graph here. So this is our money, and this is the number of units. So this is a business application. That's what I was trying to say earlier. It slipped my mind. All right. So if I do the cost function, so let me do this one in like red. Okay. And let's say this is at 35,000 and the slope's 0.85. So this is my cost function. Okay. Y equals cost function. And then my revenue function is, we'll do that one in blue. Something like this. So y equals r of x. Oops. Then where they intersect, that's called the break-even point. So that x, we're going to have the x value, and the y values are going to be equal there. Okay, so find the break-even point and the profit function. So the profit is equal to revenue minus costs. Okay, so our profit function will be 1.55x minus 0.85x plus 35,000. So distribute that minus sign. Okay, so just make both of them negative. 1.55 minus 0.85 is 0.70. X, you don't need that last zero there, but that's okay, minus 35,000. So that's our revenue or profit function. So we can find, there's two ways we can do break-even point. We can solve this system of equations, right? So since these are both y equals, you just set those equal to each other. Or you can find out when is profit equal to exactly 0. So you can solve this equation. If we do it the first way, you'll see that it'll end up being the same thing as setting the profit function equal to 0, and it'll be exactly the same. So either way, so break-even point is where costs and revenue are equal to each other. This is our break-even point. Okay, so how much do you have to sell and produce to break even? So let's see, C of X is 0.85X plus 35,000 equals R of X is 1.55X. We're going to subtract 0.85X, subtract 0.85X. So that's 0.70X, or just 0.7, and 35,000. So see, if you set this equals 0 and solve it, your first step would be to add 35,000, which will get you to here. Now we're going to divide by 0.70, 0.70. So X equals, so let's see if I move that over 1, add 1. So that would be 5, is it 500, or let's see. Let's get rid of that one. We don't need that one. So we're going to move it over 1. Move it over 1. So there'll be 5, 1, 2, 3, 4. So we need to sell 50,000 units and produce 50,000 units. And that'll be our break-even point. Okay, and then this is our profit margin. So if you were to put 50,000 units into this, into the profit function, you would see you would get $0. So you break even. Oops. And you can see that that would be 0. Okay. So there's our profit function, and there's our break-even point. Example 11, writing and solving a system of equations in 2 variables. The cost of a ticket to the circus is $25 for children and $50,000 for adults. On a certain day, attendance at the circus is $2,000. 2,000 people. And the total gate revenue is $70,000. How many children and how many adults bought tickets? So I typically like to make a table for these things. Okay, so on the top row here, I'm doing tickets, so it's one of these revenues. So if I were to buy a ticket, it's going to be the price per ticket, times the number of tickets, and you can switch these 2 columns, and then you multiply those, and that's going to get you your total revenue or cost, depending on what side of the ticket booth you're standing on. Okay. We're approaching this as revenue, so we'll do revenue. Okay, and then on the side, I'm going to do the different types of tickets I'm selling. So I got adults, children, I'll just write child, and then total. Okay, total. So let's see, the price per ticket for adults is $50. I'm just going to write, I should have just wrote 50, but that's fine. And then 25, in fact I will. And then $25 for children. And then number of tickets we don't know, so we'll call that A. Number of children, we'll call that C. And then on a certain day, we sold a total of 2,000 tickets for a total revenue of $70,000. So the way I use these charts, it just helps me organize all the information when I read it, right? So I read it the first time. I noticed, hey, this is going to be one of these. We want revenue, so it's the price per ticket times the number of tickets to get the revenue. And then you have different categories of tickets, so that goes on the side, adults and children. And then I can go back and read the problem again and start filling in this chart. So the tickets for circuits, 25 for children, so 25 for children, 50 for adults. On a certain day, the total attendance was 2,000. Total revenue was 70,000. We don't know how many adults purchased. We just know a total of 2,000. So we'll call this one A. We don't know number of children, so we just call this one C. And then I'm going to use this equation on top to fill out this last column. So 50 times A is 50A. And 25 times C is 25C. And to get a total revenue, I'm going to add how much revenue I made from adult tickets plus the money I made from children tickets. And that'll get me my total revenue of the 70,000. And remember what we said earlier on. If I have two variables, I need two equations. So this is where we get our other equation. To get a total number of tickets, you're going to take the number of adult tickets you sold plus the number of children tickets you sold to get a total attendance, paid attendance of 2,000. So this is my system. So now I'm going to solve it. I usually use the elimination method, and I typically look at the smaller of these two, which is the 25. I'm going to multiply the equation 1 by the opposite of that sign. So equation 1 times negative, the opposite of that coefficient, sorry. So negative 25. So I get negative 25A minus 25C equals 50,000, negative 50,000. And then 2, I can leave it alone. 50A plus 25C, 70,000. My new equation 3 would be 25A. 25A. The C's cancel. I get 20,000. Then I'm going to divide by 25. See, I just kind of go in automatic because once you get practice doing this, right, that's why I set up my charts. I don't have to think it's hard. I know where to get my equations, right, in the total column. Total tickets, total revenue. A plus C is 2,000, equation 1. 50A plus 25C equals 70,000, equation 2. Solve it using elimination. And I get A equals whatever that is. I think it's 800. Okay, so if there's 800 adults, how do I figure out children? Well, I'm going to plug this back into equation 1. 800 adults plus children has to be 2,000. You subtract 800, so you get 1,200 children. Okay, so how many children and how many adults? So there were 800 adults. Oops. And 1,200 children. That bought tickets that day. And that brings us to the end of this lesson. So again, practice, practice, practice. Go to the end of the section. Go to the section exercise set at the end of this section. Do all the odds. You know the drill. Do as many as you can, preferably all of them. Do some of the evens too if you have time. Anyway, have a great night, and I'll see you next time.